Okay, so let's try the next coding exercise. So open the leetcode.com and go to the problem section. And in the search question, search delete node in BST and hit enter. So there is a question number 450 and it's come under the medium category. So click on it. So let's try to read the question and then we will see how we have to solve this question. So given a root node, so we have a root node is given. So if you see this function is given delete node, and in this there is one argument root. So root node is given, and that refers to the BST. So that is the BS for the BST tree is the root node is given, and a key is given. So a key is also a given. So that is one of the argument. Delete the node. So BST is the binary search tree. Delete the node with the given key. So we need to delete the particular node with the given key. So let's suppose there is a tree. So what is the binary search tree? Binary search tree is a tree in which like the left hand side has the lower element and the right hand side has the higher element. So if we consider five, uh, if you see the left hand side of the five, they all are the lower element, and if you see the right hand side of the five, all are the highest like large element. And then if we consider three as a root, on the left hand side of the three there are small elements, and on the right hand side of the three there are large elements. So this is called as a binary tree. Then we need to delete a node from the given tree, and we need to return the root node. So let's suppose if we are like deleting three, then we don't need to just delete. All right, we need to return the full tree. That is a like main question. We need to return the full tree. Delete can be like we can anything anyone can delete, but we need to return the full node, full tree. As an example, so there is a tree 5, 3, 2, 4, 6, 7. If the key is 3, all right, then first we need to search the key. Searching is like very easy. That is the binary search tree, so we can search. We will come here. Okay, if it is 5, whether key is equal to our root dot value, no. Okay, if it is less, yes, it is less. Then we will go left. If it is more, then we will go to right. So searching is not a very complex task. Searching is very easy. So, but when we reach 3 and we need to delete, then once we get once we delete this 3 node, we need to like either put 2 here or either put 4 here, and we need to point this root element, that is the parent element, to their child elements, like one of the child elements, which is going to satisfy the BST property. So there one way we can track the parent element and we can track the child element as well. All right, so that is the iterative approach, but let's try with the recursive approach. So recursive approach is a little bit easy approach. So first try to focus what all the conditions, what all are conditions. So we have given this tree. So first condition is, because if you see the constraints, in the constraint it is mentioned the number of nodes in the tree can be 0 as well. Right, so the first constraint is like if root node itself is a null, then we don't need to do anything, we have to return null. So let's write this condition first. All right, so if root is none, then we have to return either root, because root is none, or you can say none, whatever you want to say. Okay, so one case is done. So this is case one, आपका base case, because we are doing the recursive approach. So in the recursive approach we need one base case, so that is the base case as well, and also the case one is done, completed. All right, so now let's look at the second case. Second case is there is a node that is a leaf node which we want to delete. So if we have to delete the leaf node, just delete it, that's it. Right, we don't need to point their childs because there are no childs. If you consider 2, there are no child, there are no left child, there are no right child, but to reach till 2 we need to, so here is a 2, so 2 is less than the 5, that is the root, right? So first we need to reach 2. So second condition is case 2. If key is less than root dot value, this is our second case. So let's suppose if I have to delete 2, so key is whatever the element we need to delete that is less than our root. So what we can do, if key is less than root dot value, right? So in this case it's a root dot value. Then what we can do, we can call our function on this part, on left hand side, right? So we can, because it's a recursive, so we can call self dot delete node. Then but we have to pass in a like root argument, and the root is now 3, which is root dot left. Along with we need to pass the key as well, so key is same, which is perfectly fine. So we come here, all right? Then again it will go down, so that is a different thing. Like just focus on the like level 1 only, all right? So we have called these three because like we have to call. Okay, what is the third condition? Third condition is, if you see 1 minute, if you see here, third condition is this one. If the key which we want to delete is greater than the root node. So this is our like second condition. And case 3, if key is greater than root dot value. So L, if key is greater than root dot value, if key is greater than root dot value, then what we have to do? We have to call our same function on this tree, right? Then self dot delete node root dot right, comma key, which is also fine. Okay, else. But like we are just coming here, we are not deleting because right hand, because it could be 7, it could be one more element. We are not deleting. So let's go to our case 2 first. So case 2. So this case. So let's suppose we like we first come here, right? We come first here. Like we have to call the same function delete node root dot left dot key. All right. Uh, we are calling this function. Then we will we are going again checking if root is none, so 3 is not none. Then we come here. If key is, what is key? 2. 2 is less than 3. Yes, 2 is less than 3. Then where it will come? It will come here 2. So now it is going to call this tree. Now it is going to call this tree. All right. Okay. Then it will check here. If 2 is none, no. If 2 is less than root dot value, no. If 2 is greater than 2, no. Then it should come under the else condition, where 2 is equal to 2. All right. But if 2 is equal to 2, we can, how we are going to know like this is a leaf node, because this could be the middle node as well, right? And this could be the node, this could be the node which has like one child as well, either the left child or the right child. So when the value become equal, at that time also like there are three conditions. So there are like either there are no nodes, or either there are two nodes, or either there are a single node. So what we have to do, basically, let's suppose if there is a nothing, or let's suppose, don't focus on this. Let's suppose if there is a one element, right? So we come here, we come. So let's suppose if we are calling this like 6, we call the delete function delete node root dot right dot key. So it come here, then it is going to check if it is equal to key. Okay, then what we have to check? We have to check if whether there is a left hand side or not. So in this case there is no left hand side. So let's write that same case. So if root dot left is none, So if root dot left is none, then what we have to return? What we have to return is like return means to the above function, because we are calling from the above function. So we have to return this thing, this 7, because now we have to remove 6 from here. So we have to return 7. So what we have to return? Return root dot right. We have to return a root dot right. But if it is going to return from where this function is being called, from here, delete node, because we are going on the right hand side. So if it is returning, there should be some variable to accept that. So we have to attach this 7 on the root dot right. So basically root dot right is equal to whatever the element it's going to return. So the 7 is going to return, then it will just attach like this. It will attach like this, because root dot right, one sec, what is happening? Then root dot right is equal to 7, because 7 is returning here, right? Because there is no one, there is nothing on the left hand side. So we check if there is nothing on the left hand side, then we just return 7. Now there is no connection with the 6. Now root dot right is pointing to the 7. So it just returns 7. It just returns 7. From here it just returns 7. But here we are catching. Here we are catching. Okay, whatever the root, on the whatever the root, all right, at the first level, second level, third level, whatever the root, just attach its to right. Same case, if it is left, right? So let's suppose if there are some element on the left hand side, but there is no element on the right hand side, then the same thing we have to do. Uh let's suppose let's suppose we don't have the 4 and we need to delete 2. We need to delete 3. So what we have to do? We need to attach 2 with the 5. We need to attach 2 with the 5. All right. So same case we have to check. So L if root dot right is none. If root dot right is none, so there is no element on the right hand side, but there is an element on the left hand side. So what we have, so let's go there, just ignore this 4 for the time being. Just assume 5, 3, 2, and we need to delete 3. So we come here, we see, okay, there are no right element, or there are only left element. Then we have to return 2. All right. So how we have to do? Return root dot left. If we are returning, it should accept something. So root dot left is equal to whatever is bigger. So whatever we are calling on the left hand side, so it is going to attach on the left hand root dot left. So this is the root. Our root dot left will be attaching with the 2. So now 5 is going to attach with the 2. In that case, when there is no 4. All right. Okay. So that is also done. Okay. Let me remove this. Just a second. Okay. Now we have only one case left. And what is the case? So we check, okay, like if there are no one element, two element, right? Oh, but two element cases left. So else. Okay. So else. So if there are left element as well, if there are right element as well, then let in this case, one second, let me scroll up a little bit. Yes. Now in this case, we have to delete 3. So we come here. But what should we return? Should we return left hand side? Should we return right hand side? Because 5 has to attach to some element. All right. So either 2 or either 4 or either whatever the element, and there could be like so many element like before that as well. All right. So to whom it is going to attach? To whom the 5 is going to attach? Because we right now 5 is with attaching with the like 3. So but 3 has been deleted. So instead of deleting, we are just like what we are going to do is, let's suppose here there is some value. We what we can do is, like, we will just replace that value with that instead of deleting that node, right? So what we have to do is, so there are two possible solution, and whatever, like, it's up to you, whatever you want to do. So in this case, let's suppose if we move 4 above, right, then is it satisfying the BST property? Yes. Is it satisfying? If we move 2 above, then it is also still satisfying the property. So basically what we have to do, if we move the element from the left hand side, or if we move the element from the right hand side, on what basis we are going to move that element? So let's suppose if we are going to move the element on the from the left hand side, on the left hand side, because we know if we are moving here, so 3 is bigger than all the elements of the left hand side, right? All the elements of the left hand side. So where we can find the the bigger element? So on the right hand side of the two, the top last right hand side of the two, there should be the bigger like element. So let's suppose there is a one element. Just assume 1 second. Just assume there is a one element x here. There is a one more element y here. There is a element here a here. There is a one more element b here. So instead of 3, and if we want from this tree we want to keep some element here, but which element should we put? 2. If we put 2 here, right, then it is not satisfying the property, because if we put 2 here, then it is violating the BST, because on the left hand side all the elements should be small, but x and y are the greater than the 2. So what we have to do, we have to find the greater element from this side, from this true. Or if we have to pick the element from the right hand side tree, let's put right, we need to pick the smallest element, because the right hand side elements are the more, so we need to pick the smallest element. All right, so let's write a function. So if we have the left node as well, right node as well, then first we need to find a self dot find minimum value node. And so it's up to you. Either you find the minimum value or either you find the maximum value. So if you find the maximum value, then you need to find from the left hand side. If you want to find the minimum value, then you need to find from the right hand side. So let's suppose I am finding the minimum value. So find minimum value of the node. So I have to find from the right hand side. All right. So I have to pass root dot right. All right. So let's write this function. Def self node. Okay. Now how we are going to find the let's suppose there are some elements here. There are some elements here. X, then so many elements. Then how we are going to find the element? We are just moving right. We just like run a while loop and we are keep moving right. So while node dot, sorry. We need to find the minimum element. So minimum element is on the left hand side, on the left hand side. So we need to find, if while node dot left is not none. All right, we have to do node is equal to node dot left, and once completed we need to return the node. So we get the node. So let's suppose we find some element, then what we have to do, let's suppose in this case, so let's suppose we find 4 as the smallest element. Then what we have to do, so instead of 3 we need to just put 4. So right now root is 3, we need to put 4. So what we can do, we can just replace the value root dot value, which is 3 right now. We can put temp dot value. So temp is 4, so it returns my this function returns some value, and but let's suppose it return 4. So I am just putting this value. So if I just put 4 here, right, then I am not deleting the 4 here. So 4 is also here as it is. Now I need to delete it, because now 4 is duplicate. I need to delete 4 because 4 already shifted here. So how I am going to delete this? Delete function already there. So now what I will do is self dot self dot, okay, delete node, self.delete node on the right hand side. We need to find on the right hand side root dot write, and it is accepting the key. What is the key? Key is temp dot value, because temp is 4 or whatever the element may be, 4.5, 6.5, like any element, like 4.1, 4.2, 4.3, or any element, it will come, it will give. We have to delete that. So that's why, like, voice, whatever the element we need to delete, that we need to pass in the function. So right now we have to delete 4. So that's why we are passing the temp dot value. Now it is going to return something. It is going to return something, and we need to attach with that root. So it is going to, we can find root dot write is equal to self dot delete mode. And finally, we need to return the root node. Why root node? Because in the question, it is being said we need to return the full tree. So it looks okay. So let's try to run if it's working or not. Okay. So there are some error, ROR. So it should be root. So our, like, test case has been accepted. So let's try to submit it. So our solution has been accepted, though it took like very less time, because we are like using the recursion. So it is taking like space as well, and recursion took like definitely a time. So we can do with the iterative approach, maybe in some other video, but this is like for the recursion approach. So this is like, you can't say like it's very hard question. So yes, definitely you can say it's a medium category question, and we just follow the property of the BST tree, whether we need to move left or whether we need to move right. So the same thing we are doing here. So we are just like checking all our like case scenario. So first case scenario, if root is null, then we are going to return none. Okay, then the second case scenario, the key element which we have to delete is less than the root, then we just call the same function on the left hand side. If it is greater, then we have to call the same function on the right hand side. And then once we get that to that particular element, then we have to take some decision. So let's suppose either 2, either 3, or either 6. So we point to that element, then we have to check if it is only one, if there is a no left hand side, then what we can do, we have to just return the right hand side. The same thing we are doing, if there is no left hand side, then we have to return right hand side. And if there are no right hand side, we have to return the left hand side. Otherwise, we have to do, if there are both elements, then we have to figure it out whether which element we need to put here. So it's up to us. If we want to put from the left hand side, then we found the maximum value, because like this element is the maximum, and to maintain that property, the left hand side element should be maximum, the parent should be maximum. And if we are picking from the right hand side, then we find the minimum element. Same thing we are finding, so minimum element, so we find the minimum element. Then now we need to replace it. So we just replace the value, root dot value, temp dot value. But now there are two duplicates, so to remove the duplicates, we are calling the same function, and whatever it is going to return, we are just attaching with the root. So that's it, that's the end of the video. You can also try this question. Thank you.